Okay, now it's time. Yeah, it makes me feel sorry to say that now it will be the very last lecture of Elisabeth, but all good things come to end, unfortunately. So please, Elisabeth.
Thank you, Dima. Thanks. I will briefly finish with a little bit of things that are connected, what I've been talking about so far, but then I wanted to not do too much about this, not as much as I had planned, so that I finally get to talking a little bit at least about random polytopes. I'm sorry it took me much longer to do the previous things that I had thought, but hopefully we'll get to see at least a little bit of random polytopes.
Maybe because of because of my stupid questions. Sorry, it took much time.
Of course not. I'm happy to have questions. Of course not. Don't say that. So let's finish up the things from that are connected to this affine surface area and floating bodies and are kind of related. So the thing that I want to mention is that there is a kind of dual concept to a floating body. So there exists a kind of dual concept to floating body, which I called the illumination body. So how is this defined? So we look at a convex body K again, and then we'll take all X, or we'll take an X that's not necessarily in K, and we'll take, actually those are the relevant ones, the ones that are not in K, and then we'll take the convex hull. So we look at the convex hull of X and K, which I'll denote like so. And how do we choose the X? We choose the X so that this volume here, that is the volume of this convex hull without K, this volume is delta or smaller or equal than delta. And then the illumination body, K delta, I'll put the delta on the top. This is the set of all X, so that exactly this happens, that is that the volume of the convex hull of X and K without K, that this is more or equal than delta. So we take all those. And this is our K delta, and one can in fact show that K delta is convex. And there is also, it has the same behavior if we consider a variation of volume, or the volume difference now between the illumination body and the body, and divide by the same delta to reason with the same power as delta goes to 0, then this limit also exists. So that was limit exists and is equal to some constant that depends only on the dimension, which we know exactly, and also this integral over the generalized Gauss curvature, which is the affine surface area. And we see, so the same result holds. So this illumination body could also be used with this limit as a definition of the affine surface area. And this is a kind of dual notion, because what we do here is we add on sets of volume delta, whereas with the floating body, we chopped off sets of volume delta. In that sense, it is a kind of dual notion, but it can be made more precise as well. There is also a notion of weighted floating bodies, which I do not want to mention. I just want to mention one last thing, and those are the LP, the LP affine surface areas, or P affine surface areas. Sorry about that. Now I get texts from all my friends about the elections, so it's probably going to bling a couple of times. So LPF and surface areas, we look at that for the range of minus infinity, smaller or equal than P, smaller or equal than plus infinity, and P has to be different from minus N. And how is this LPF and surface area defined? For a convex body K, it is something that's familiar to us by now, the integral over the boundary of K, and then we'll take the Gauss curvature or generalized Gauss curvature again and raise it to the power P over N plus P now. And then, but then we have an additional term. So we'll divide by the inner product of boundary point X with its outer normal, and that gets raised to the power NP minus 1 over N plus P. So that's in the exponent. Sorry, it's yeah, it's a bit. And we integrate with respect to the usual surface area measure, mu k. So we see that P should be different from minus N, because otherwise we'll get a problem here in the denominator. And what else do we notice? Well, this P affine surface areas has still almost all the nice, it basically has all the same properties as the affine surface area had. That is, there is an affine isoperimetric inequality, but now because of that term here, we cannot expect that it is affine invariant. It's only invariant under linear maps, because this term in the denominator, so to speak, fixes the origin. And in general, if we look at P affine surface area, we assume that the body is such that 0 is in the interior of K. Okay, let's put this into context. Namely, let's look at P equals 1. So let's look at the 1 affine surface area, and then we'll see that the term in the bottom disappears. And we'll end up with our familiar affine surface area that we had looked at so far. There is other things that I want you to notice, namely, if we look at the 0 affine surface area, what happens? Well, what happens is that what happens is that the Gauss curvature term disappears, and we end up with, well, P is equal to 0. So we'll just end up with the integral over the boundary of K of this inner product. And we had seen that this is equal, so we had seen that this is actually equal N times the volume of K. And we can look also at P equals plus minus infinity, and we'll get that for both plus or minus infinity, the infinity affine surface area of K is equal to at least, is equal to N times the volume of the polar body of K. So in a sense, this P affine surface area ranges from the volume of the body going over the usual affine surface area, the case P equals 1, to the volume of the polar body. And it has also many, or still almost all those nice properties as the usual affine surface area had. Good, so with this I want to finish, and if there is time at this first part, and if there is time in the end, I'll come to the open problems then. So now let's move to the second part, which is approximation of convex bodies by polytopes. Okay, so there is a huge amount of literature on that, and typical question one asks there is, okay, how, well, typical questions are, okay, we have a convex body, we want to approximate it by an inscribed polytope with a fixed number of vertices, we want to approximate it by a circumscribed polytope with a fixed number of facets, that is n-1 dimensional faces, or even more generally, we want to look at approximation of a convex body by a polytope with a fixed number of k faces. And then one wants to find like the optimal dependence on all the parameters involved, which is the body itself, the dimension, and the number of vertices or faces or I faces or k faces that we picked. And how good the approximation is measured in various metrics. So various metrics have been considered. The one that we are looking at, the only one that we are looking at here will be the symmetric difference metric, or as we are mostly just concerned with polytopes that are contained in the given convex body K, the symmetric difference metric becomes the difference of the volumes. I want to start with the first approximation result, where we actually have an algorithm, or we get an algorithm that constructs for us an approximating polytope. And so that is 2, 1. That's called the floating body algorithm, which will provide us with an approximating polytope for a given convex body K, and it will provide us with a polytope that sits in K. So this this is due to Carsten Schütt, this floating body algorithm. So I'll describe it. I'll start to describe the algorithm. So we have a convex body K. And what we'll do, so K is given. And also the floating body K delta is given. So here is the floating body inside K. And then we'll, the first step is we pick any x1 on the boundary of K. So choose x1 on the boundary of K. So let's say here. So here I've chosen an x1. Then the second step will be that we'll choose a hyperplane H2 such that x1 is in the interior of H2 minus, what did I said plus for this, so let's keep it that way. So that x1 is in the interior of H2 plus, such that the floating body is contained also in H2 plus. So we choose the hyperplane, for instance, like so. So this is our hyperplane H2. We have the two half spaces H2 plus and H2 minus. And now so now comes the third step. So that was the first step, second step. Now comes the third step. We'll choose x2 on the boundary of K, and in the other half space determined by H2, namely we'll choose it in H2 minus, in such a way that in a sense it is furthest away from this hyperplane. Like if we would move H2 to get a support hyperplane to the body, then we'll take, for instance, this x2. So such that so for instance, I could describe this as follows. So we'll choose x2 as so that in a sense, if we take the support hyperplane to the body, a support hyperplane that is parallel to the H2 that we chose, we want we want to pick a support hyperplane. And in this sense, if we choose an x2 in here, that is on this parallel shifted hyperplane, it is furthest away from this H2. So we'll choose it like so, such that, so I could describe that also like so, that the normal, maybe I write now the normal to K in X2 is also is normal to the hyperplane H2. So that we do to get the X2, and then we continue the process. Is clear how we do? So we continue the process, and we get points x1 up to xk minus 1. Before I write that, let's right away notice that if so by construction, by choice of H2, because it is a support hyperplane to K delta, we of course have that H2 minus intersected K has volume bigger or equal than delta. So let's note that also right away. This is because H2 is a support hyperplane to the floating body. So we keep going with the process, and we'll get points x1 up to xk minus 1, such that, and hyperplanes h2 up to hk, such that what happens? Okay, so no, let me start again. So suppose we have, so we continue the process. So I want to now suppose we have chosen x1 up to xk minus 1. How do we choose? Now we want to choose, choose xk. So what do we do? So we'll have, again, our body, and we'll have the floating body inside. We have chosen x1, x2, and so on. And then we'll have xk minus 1 here. So then what do we do? So so we have chosen those points, x1 up to xk minus 1, and next we'll choose a hyperplane. We choose a hyperplane. HK, such that what happens? Such that x1 up to xk minus 1 are all in, so maybe I write it as a set, they are all sitting in HK plus. K delta sits in HK plus. Okay, so for instance, we could choose the hyperplane and HK is a support hyperplane to K delta. So for instance, we could choose the, let me move this point a little bit, otherwise I cannot draw it too well. So the xk minus 1 is here. So we could, for instance, choose the hyperplane HK like so. Here
we assume that it is possible, right?
If it is possible, we do that, yeah. If we can continue the process.
Oh,
so
okay. Mm-hmm.
If we can still, if it's not possible to do all that, what we are describing now for the hyperplane HK and for the point HK, then we have stopped already, right?
Okay.
But we'll continue doing this as long as we can do that, and we'll see in a moment how long we can do that before we have to stop. So if we can still do that, we'll choose this hyperplane HK. And then we pick. So I have said everything that I needed to say. This is in here, this is in here, and then we choose a point. So I should have said that also in the boundary of K intersected with HK. So here we have HK plus, and here we have HK minus, inter HK minus, such that the normal in xk is a normal to hk. So for instance, we, or in other words, as I described it, we look at the parallel hyperplane to hk that supports the convex body K, and then we'll pick a point xk that sits on the boundary of K and on the support hyperplane. By the way, I'm talking here about a normal to the to a boundary point. We don't really care if the normal is unique or not. If we have a corner that is, if the xk is like so, we'll just choose one of the normals that are there. So we don't really care about uniqueness of the normal.
Sorry, and I miss one thing. There are infinitely many HK which satisfy this condition. How do we choose one arbitrary?
Oh, we choose just one that has this property.
Okay.
We just, maybe it's, yeah, we choose just one. We don't care which one, we'll just.
Okay.
Yeah. Maybe it will be illuminating to look at what happens if we, so as an example, before I analyze when the process stops, let's look at an example, at the example of the cube or the square in the plane. So square in the plane, what happens? So say, square, actually I want the L infinity, two-dimensional L infinity ball, because for this one we know how our floating body looks. So we know that the floating body here looks like so. Okay, so that's the floating body. And suppose we have started here. That is our x1 that we choose. Okay, good. Then we can choose as our first hyperplane this one. That's our h1. Then we could choose, as you said, there are many choices for x2. So for instance, we could choose any point here, but we could choose, so for instance, we could choose this as our x2. Then we can keep going. We take as our next hyperplane, sorry, that's h2. We take as our hyperplane h3 this one, and again we have many possibilities to choose the x3. Say we pick this one as the x3, then we'll have as our next hyperplane, we'll have this one, which is h4, and we'll pick x4 here. And then we notice, is the process really finished, or can we still pick a hyperplane so that all the conditions that I've mentioned hold? And we see that is in fact so, because for instance, we can choose this hyperplane, h5, I write it here. We can choose this hyperplane. All the points that we have previously chosen are in the 1/2 space defined by the hyperplane. It's a support hyperplane to the floating body. And we can pick as a x5 this point here. So we have picked this point as an x5. Then is it stopped, or can we continue? Well, we see that we can continue because we can choose this as an h6 hyperplane. All the points previously chosen are in the other half space, and we can choose a point that is on the boundary of the square and in the other half space determined by this hyperplane h6, like so. And in fact, it turns out that these points and these points can be chosen as well, and then the process stops. So if we started out with that as our starting point, then we actually have that many points that I have indicated before the process stops. However, if we have another scenario, namely, okay, let's look at another scenario where we have our floating body here, and where we have not started here, but that was our starting point. Then, okay, so we started here. Now we'll have to choose a hyperplane. We cannot, of course, so a hyperplane that we now choose typically would look like so. So it would be this hyperplane. This is a support hyperplane to the floating body. In 1/2 space sits the points that we have chosen. We cannot choose this as a support hyperplane. We cannot choose now this as a support hyperplane because this point sits in the other half space. It should sit in the same half space as the floating body sits. So we cannot take this hyperplane. We'll have to, so that's our x1. We'll have to take this as our h2. And for instance, we'll take, we could take that one or that one, but we could not take this one or that one. We have to take as our x2 this one, because we want the point that is, if we take a hyperplane that's parallel to the chosen one, we want and that's a support hyperplane of the body. We only have the choice to choose this point x2 and so on. Now the next step, so we have chosen x2. Now the next step would be to choose this hyperplane, and we'll necessarily have to take this as our x3. And the next step would be to choose that hyperplane, and the necessarily choice for x4 would be this one. So we see that, and then it's finished. So we see that, and then the process is finished. So we see that, okay, it depends very much on the choice of our starting point. If we were unlucky and started here, that is at that red point here, we would have to spend much more time, or we would have to choose many more points than if we had started with this a starting point here, which finishes the process much faster. Good. So now let's actually decide what's the number of points that we need to pick so that the process finishes. So how many points? How many points do we choose? Or can we choose? So let's, so before the process stops. So let's draw a picture again, and let's see how we can decide this. So our x1, say, was here. I also have to draw the floating body, which is here. And we haven't had a hyperplane H1, so let's get a hyperplane H1 also. Let's say we have a support hyperplane here to x1, then I'll look at a hyperplane that's parallel to the support hyperplane to k in x1 and shift it till it becomes a support hyperplane to the floating body. That will be our h1. We had an x2 here. I have to be careful with the hyperplane I'm choosing. So we had an x2 here, which should have drawn a bigger picture. Okay, let's see how good the picture is, and if it's not good enough, then I'll draw another one. So we had an x2 here, and so on. So what we observe by construction, because the hyperplanes HK were all supporting hyperplanes to the floating body, if now we look at the convex hull, so what we are looking at is the convex hull. I think convex hull I denoted without this now. So if we look at the convex hull of xk with k delta and intersect it with hk minus, so what is it that we look at? So for instance, if k is equal to 1, what we look at, we'll take the convex hull, let me do blue now, we'll take the convex hull of x with a floating body, and then we'll intersect it with hk minus. So h1 minus is here, so what we get is this cone. So that's what we get when k is equal to 1. So we do that for all k. So let's do that also for, say, k equals 2 on the picture. So I'll do convex hull of x2 and the floating body and intersect it with h2 minus. So h2 minus is here. So I'll get this cone now. And we see by construction, because those hyperplanes were supporting hyperplanes to the floating body, we see that this set or this cone intersected with hk plus 1, k delta, the convex hull of xk plus 1, with k delta intersected hk plus 1 minus this intersection is empty, like I have indicated here in the picture. So that's the first observation. So note first this one. Now the second observation that we want to make, and that's actually, yeah, most of the work. if we look at the volume of such a blue cone here, so these blue cones here, and if we look at the, if we try to compute, or if we compute the volume of these blue cones, these are of the order delta, modulo a constant that depends on the dimension. They are of the order delta. So this tells us that, okay, say we, so now we come to the questions, how many points can we choose? So how many points before the process stops can we choose? Say we choose, so what's the number? The number n of points that we can choose is such that n times delta is equal to, well, each of those things here has roughly volume delta. So it's the sum, k goes from 1 to capital N, of the volume of hk, the convex hull, hk minus, which is equal to, because those are all disjoint, which is equal to, because those sets are all disjoint, it's equal to the volume of the union, k goes from 1 to n, of these cones. And of course, we have to stop when the volume of these cones fills up. When the volume of these cones fills up all these set that is the different set between k and k delta. So that's when we have to stop, when this is of the order of volume of k minus k delta. So this tells us what our n is, namely n is of the order k without k delta divided by a volume divided by delta. Then we'll have, so then taking the chosen now capital N points, so taking these chosen capital N points where we now know how the n is related to k and to delta, we'll take the convex hull. So Pn is the convex hull of these capital N chosen points, and that is so Pn approximates k, and we'll see in which sense we mean it approximates k. So I have said that now, and we note that actually Pn is contained in k. This is obvious, but it's also like so that Pn contains the floating body. So the floating body sits actually in Pn. So this approximating polytope is squeezed in between the floating body and the body. So why does it contain? Why does the Pn contain? This is obvious. So why does it contain the floating body? So let's see. So we show k delta is contained in Pn. So suppose not. So yeah, suppose not. Then there is a x delta, say, in k delta, such that x delta is not in Pn. So picture is like so. So here is our floating body. And okay, here is our Pn. So here is our Pn. And we find an x delta, or need not be on the boundary, but we'll find such an X delta so that the things look like so. But then we know by the separation theorem, by Hahn-Banach theorem, by separation of convex sets, or convex set and a point, separation theorem, there exists a hyperplane H such that X delta is in one of the half spaces, say H minus, and Pn is in the other half space, H plus. So we find such a separating hyperplane. Well, need not be parallel to the, okay, and I've started to draw it like so, but it of course need not be parallel to this face of the polytope. So this is the separating hyperplane H. Then what do we do? So what do we do is we move H so that it becomes a support hyperplane to the floating body. And actually we move it more so that it becomes a support hyperplane. So it becomes a support hyperplane. Let's call this H twiddle. So we move H parallel to get the support hyperplane to K, which I've called a twiddle. And then we can repeat the process and we find a point, or we choose a point x n plus 1 on H twiddle intersected with the boundary of K. And this xn together with this hyperplane that I have moved to this first one here, I don't know, maybe H bar, together with this hyperplane H satisfies all the assumptions, all the conditions of the construction, and that is because all the other chosen points, which are the points of the polytope, all the other chosen points sit in the hyperplane H plus, and the floating body sits in the hyperplane in the half space H plus, and this xn plus 1 sits here on the boundary intersected with this shifted intersected with this H twiddle. So we can get another point, and that contradicts that n was the maximum number of points chosen because the process had finished with the number n. So yes, so that shows us that indeed the floating body is contained in this polytope that we have chosen with this floating body algorithm. And now let me give, so that was the idea of the construction. Now let me give the precise formulation of the theorem. So theorem, let's do to Carsten. So K is a convex body in Rn. I'm not writing, so for all delta smaller or equal than the volume of K divided by 4e to the 4, I'll give you all the constants. There is sorry about that, an n in n, a natural number, such that, so we'll have an estimate for this natural number n. This is the number of points that we can choose before the process finishes. So that for all n, and n, this number when the process finishes, the number of points we can choose is smaller or equal than e to the 16n. K without K delta, the volume, divided by delta to the delta times the volume of the Euclidean unit ball. So this is an estimate on the size of n, and there is a polytope Pn with at most n vortices, such that k delta is contained in Pn, is contained in K, and this polytope Pn we'll get by this floating body algorithm that I tried to explain in the previous pages. So the approximation of the body with this floating body algorithm polytope is given by this, and now we want to see how good this approximation is. That is, we want to see, in the symmetric difference metric, how close or how small the symmetric difference metric is between this approximating polytope Pn and the body K. So to see that, let's recall our theorem that I tried to prove the last 3 times, which is this volume difference of the body and the floating body, because this polytope, this approximating polytope, is now squeezed in between that. So we know from our previous lectures that this volume difference divided by delta to the 2 over n plus 1, as delta goes to 0, is this constant Cn, and I'm writing it because I want to now it's n plus 1 on the top. Never know, sometimes I put the constant on the other side, then I never know what's on the top and what's on the bottom. So it's 2 to the n plus 1. And then we'll have here the affine surface area of K. So we want to see how good the approximation is. Now, this, as we see, makes only sense in a situation where actually the affine surface area is different from 0. So we'll look at a convex body K. So let K be such the affine surface area of K is strictly positive. All right, so what is it that we are doing here? So we know that if delta goes to 0, this difference here approaches that limit. Notice that this quantity here is, at least in high dimensions, which is the situation we are interested in. This is proportional to a constant times the dimension. So our constant that we usually denote it by Cn is just a constant times dimension. So as this quotient here, as delta goes to 0, this approaches constant times dimension times the affine surface area of K. So for delta small, we get that. But what does it mean, delta small? It means if we go back up here to our choice of the number of vertices that we chose for our approximating polytope, we see that, okay, if we consider a situation where delta is small, delta goes to 0, that means that actually the number of vertices increases. So how good this approximation result is, we are actually seeing in a, so to speak, asymptotic situation where the number of vertices is large. Okay, so what? Okay. So unfortunately, I need another page, but we need the theorem. But maybe you'll remember. So by the theorem, so now we have, so to speak, delta very small fixed. Then by the theorem, there is n, which is of the order, I'm writing it, it was e to the 16n, and then the volume difference k without k delta divided by delta times the volume of the Euclidean unit ball, and the polytope Pn with at most n vortices, such that what happens? Such that k delta is contained in Pn, and that contains k. So consequently, we get, now we look at the volume difference between the convex body and this approximating polytope. That's how we measure how good the approximation is, and also we'll divide by n to the minus 2 over n minus 1. Because, and that's why it was important that we really make sure that the floating body sits, is a subset of this approximating polytope. This is of course smaller or equal than k without k delta, the volume divided by, well, here I don't change anything, but now we use, this is roughly k without k delta, and now we use that n is of this order here. So n is of this order, so I'll plug that in now. So we'll get what? We'll get a delta to the 2 over n minus 1, the Euclidean ball to the 2 over n minus 1. And then on the top, we'll have, we'll have another e to the 32 n over n minus 1. And then we'll have another k minus k delta to the n to the 2 over n minus 1, which gives us a total of k, the volume difference between the body and the floating body, of to the power n plus 1 over n minus 1. Yes. Yes. So we have this. Now I want to rewrite this a little bit. So this is the same as k without k delta to the delta over to the 2 over n plus 1, and the whole thing to the n plus 1 over n minus 1, right? Because the power of delta is SO, but if I bring in the power of delta we are interested in order to apply our theorem, it's this expression that we want. And then we'll have just actually a constant times n, because, okay, e to the 32 over to the n over n minus 1, this is a constant, and the volume of the Euclidean unit ball raised to the power 2 over n minus 1, this is of the order 1 over n, so it's in the bottom, so we'll get an n here. Now let's bring in what we had said, that what happens when delta is small. We know that this quantity here converges to the affine surface area of k times another constant times n. So we'll get that this is smaller or equal than another constant. I'll call it again n, and then again c, and then we'll get n squared, and then we'll get here the affine surface area of k to the n plus 1 over n minus 1. So it's the affine surface area that seems to come in naturally in such questions of approximation of convex bodies by polytopes, but maybe in that case it's not so surprising because we have used the floating body algorithm, and we know that the floating body is intimately connected to the affine surface area. So it's maybe not so surprising that it comes in at that point. But what I want to do now is also the result that we get, our approximation result with this polytope given to us by this floating body algorithm, is this one. Now we want to see how good is this approximation. So how good is this? Because as I said, when one approximates a convex body by polytopes, one kind of always wants the optimal dimension, the optimal dependence on all the parameters involved, like the dimension, like the body, like the number of vertices or facets or whatever we have chosen, that is this quantity here. So, and to see this, we need, we get to our next point, which is, so that's 2, 1. And mostly what I want to do is compare the result, this result, to results about random polytopes. So random polytopes. So what do we look at when we look at random polytopes? So what's a random? First, the definition: a random polytope. How do I call it? Well, is the convex hull? I didn't call it. Of n, say randomly IID chosen points in Rn with respect to a probability measure. With respect to a probability measure, and we call, so I'll call this random polytope the convex, I'll call it Pn, and it's the convex hull of this capital N randomly chosen points. Now, what are typical setups? So a typical setting is that the endpoints are chosen at random with respect to the normalized Lebesgue measure. Let me write it M over the volume of K, or M of K. So the points, the endpoints are chosen at random with respect to the normalized Lebesgue measure in a convex body K. So that looks like so. We have our convex body, and we'll choose endpoints, and we'll take the convex hull, and then we'll get a random polytope Pn that sits in K. But that is maybe not the best choice or the best thing to do, because we notice that not all points chosen become vertices of the polytope. For instance, this one doesn't become a vertex, so we are wasting points. So it would be much more economically to choose the points. So choose the points on the boundary of the body instead. That is right. It looks like so. We choose the points on the boundary as the floating body algorithm did. And then we get that every point chosen becomes actually a vertex of the approximating polytope. There is a third situation which I probably will not have time to discuss, but which is actually having some improvements on the previous two, even on the second one. What one could do is one could choose, so to speak, okay, so this situation that I just showed and this situation here produces approximating polytopes that are inside the body. So one end, so the setting 1, 2 produces approximating polytopes inside K. One could think of another scenario. One could think of an arbitrary position polytope but I will not discuss this, but just as an aside. So an arbitrary position polytope, which is neither inside nor well, what one does usually when one considers the facet circumscribed, but really arbitrarily positioned, say like so. And this has some advantages. It gives actually an improvement on the dependence of the dimension, but I will not. And then it's really the symmetric difference metric that one looks at. But I will probably not have time to do this. So what we want to concentrate on, we'll concentrate on the case 2. And so let me make specific what we'll do. So we will choose endpoints on the boundary of a convex body K with respect to a probability measure. I'll denote it by PF. So what is PF? It's the surface area measure where F is a function a continuous, strictly positive function defined on the boundary of K. And we want a probability measure, so we should have that F d mu is equal to 1. So we'll choose the points with respect to such a measure. Then we want to measure. So we choose this. We take we choose the points on the boundary of the convex body with respect to this measure. Choose capital N points. Take the convex hull, and then we'll get a random polytope. And now we want to see how well is this approximating polytope, or how well is this random polytope approximating the body in the symmetric difference metric. So to know that, we need to know what's the expected volume of such a random polytope. So the expected volume of the random polytope of such a random polytope is, that's notation again. So expected volume of n chosen points on the boundary of K with respect to this probability measure. This is the integral over the boundary, the n, capital N-fold integral over the boundary of K of what the volume of the convex hull of the capital N chosen points. So we have chosen capital N points x1 up to xn. We take the volume, and each point was chosen with respect to this probability measure xn. So this is the volume of such a random polytope. Then if we look at the volume difference of the body and this volume of this random polytope, which we have written here, then we'll get how well this random polytope approximates the body in the symmetric difference metric. So let me write down the theorem which gives us this. And this is Carsten and myself. Okay. But then also under other assumptions or stronger assumptions, it was also proved by Matthias Reitzler. Okay, and okay, in the specific case, when K is the Euclidean unit ball, it was proved by, maybe I should write that. In the case when K is the Euclidean unit ball, it was proved by Josef Müller. So what does the theorem say? And I'll give them most with the least I like the strongest formulation. So let K be a convex body oops, should hurry. Such that now we do need some smoothness condition. They are not very strong, but some smoothness condition are needed, such that there exists a small r and a capital R. So the small r is strictly bigger than 0, smaller equal than the capital R, smaller than infinity, such that for all x in the boundary of K, we'll have the following happening. If we look at the little ball, and we've seen such conditions when we've discussed, in the last 3 times lectures, we have seen such conditions. If we look at the ball that is centered at x minus r nx, R, that should be contained in K, but now we'll have, and those conditions that we have seen, but now we also need a condition from the other side, namely that if we look at the big ball, so to speak, then this big ball should contain K. So picture is like so. So we need some smoothness assumptions on the boundary. So we'll find a little r so that the ball that's centered here at x minus r nx is contained in the body, and we'll find a capital R so that the big ball centered here contains K. And that should happen for every boundary point. So we need some smoothness condition. This smoothness condition is, one can show that it is weaker than C2 plus. So when we have this, then, so assume we have this, then the limit as the number of chosen points goes to infinity. So this is an asymptotic result of the volume difference of K and the expected volume. How did I denote it? Expected volume of n chosen points, points chosen on the boundary with respect to this probability measure, divided by n to the minus 2 over n minus 1. This limit, one can show, exists and is equal to some constant that depends only on the dimension. I'll call it dn times the integral over the boundary of K, and then comes the Gauss curvature or generalized Gauss curvature raised to the power n minus 1. We integrate as usual with respect to the usual surface area measure, and we'll divide by the function f raised to the power 2 over n minus 1. Because the function f should come in somewhere, because it's the density of the measure with respect to which we choose the points. So I'll now make a few remarks, and then we'll compare it to our previous result. So firstly is that we know dn explicitly. It's just some combination of gamma functions. I want to put this result, as I said earlier, one kind of believes that if one chooses the points inside the body instead of choosing them on the boundary, one wastes points. So let's now see. So we have this result here when we choose the points of the approximating polytope on the boundary. Let's see what happens when the points are chosen in K with respect to the normalized. Let's not bring in a function f, let's choose them with respect to the normalized Lebesgue measure. And then what one gets is that the volume difference, how did I write? So let's write it like so then. So we choose the points, we choose capital N points in K with respect to the normalized Lebesgue measure. This behaves like as n goes to infinity, so it's also an asymptotic result, some constant beta n times the affine surface area of K times the volume of K over n, and now this gets raised to the power 2 over n plus 2 over n plus 1. Sorry about squeezing this like so. So we see, so what do I want to what I want you to observe here is that here we'll have the power, the number of chosen points here gets the power 2 over n minus 1, whereas the number of chosen points here gets the power 2 over n plus 1. So this is worse than that one, which is not surprising because exactly this phenomenon happens. Not every point chosen becomes a vertex. So, so that's one thing, comparing, seeing that, okay, choosing the points on the boundary really makes a difference, namely a difference in that case on the dependence of the number of points chosen. Then the other thing that I want to notice or remark on is, let's look at this quantity that we have on the right-hand side. So it's a natural question to ask for which f is the right-hand side minimum. And the answer is that this happens for f, let me give it, let me write fa. That happens if we take the f where the points are chosen according to curvature. That is, if we pick as fx to be Gauss curvature or generalized Gauss curvature raised to the power 1 over n plus 1 divided by the affine surface area of k. I have to divide by the affine surface area, so that we'll get a probability measure. And it is normal that such a choice of the function f should give us the optimal result, that is the right-hand side becomes minimal, because if we think about how we choose, how we should most economically choose the points, we see that, okay, where the body is flat, we should not choose as many points to get the same good approximation in the symmetric difference metric, that is the volume that's between the body and the approximating polytope. Whereas where the body is very curved, we should put more points to get the same good approximation in the symmetric difference metric. So if we have chosen this FA, what happens? How is now then this limit behaving as n goes to infinity? That is, how does the expected volume of such a random polytope now behave if we choose capital N points on the boundary with respect to this optimal choice of the density? Then what we'll see is we'll get, so it's our dn, and then we'll get what? So if I put everything in, I'll get, so we'll have kappa to the 1 over n minus 1, and then we'll have our function, which is this one. So we'll get f, which is kappa, to the 1 over n plus 1, but that gets raised to the power 2 over n minus 1. And then we'll have d mu k, and then we'll have the affine surface area of k, which, because it goes with the f, we have to raise to the power 2 over n minus 1. And if we put everything together, what we'll get is just this constant dn times the affine surface area of k raised to the power n plus 1 over n minus 1. So that's what we get. If we, now let's first compare, maybe I'll say this first. So there is this, so what I want to do now is remember the result that we had when we looked at our approximating polytope that was given to us by the floating body algorithm. So floating body algorithm provided us with a Pn such that the with a Pn we had said such that the volume difference and we had the same dependence. As we have now in this random approximation, we have the same dependence concerning the vertices, and what we got was a constant times n squared, but then we had the same expression as far as the as far as the dependence on the body comes in, namely the dependence comes in via this affine surface area of K. So that's why we were talking and discussing affine surface area in the first place, because well, we already saw in the floating body algorithm that naturally affine surface area came in, but that maybe was not so surprising. What we see now in this general approximation of convex bodies by random polytopes, naturally also this affine surface area comes in. Okay, and the way we had established this result here was also an asymptotic result, because we had chosen delta small, which meant that n was large, that is, n was going to infinity, because delta was going to 0. So now let's compare this random order of magnitude, or the order of magnitude that we get from this random approximation with the one given to us by the floating body algorithm. So this coincides. So the difference is potentially only in this, comparing this constant dm with the n squared. And that's, so this is optimal, this is optimal. This, maybe I shouldn't say it at that point yet that it's optimal, because we don't see this yet. We will see this in a second. So where there could be a potential difference is only in when we are comparing the dependence on the dimension. So here we have n squared, and actually one can show the dn is of the order n. So in the dimension dependence, this floating algorithm is not as good. And that to show that this no, one can show that this is of the, that the dn is of the order n. Okay, now in the final time I have, I want to write this. So the random result again. So choosing points at random with respect to this optimal probability density as n large gave us this dn, I called it, and then the affine surface area of K to the n minus 1 at n plus 1 over n minus 1. So that was the random result. Now, what I want to do is I want to compare this. So compare this to the best approximation result. That is, we want to look at, okay, if we keep choosing, if we let go the number of vertices that we choose towards infinity, what happens, what can we expect, how the best approximating polytope approximates the body in the symmetric difference metric. And the theorem of this theorem about best approximation is due to McClure and Vitale in dimension 2, and Gruber for dimension bigger or equal than 3, and K is C2 plus. Then same thing, we look at, well, let me write how I've written it up here. We look at the volume difference of a body, of the body K, and minus the now best approximating polytope inside K with n vertices. We divide by the same quantity n to the minus 2 over n minus 1. This, as n goes to infinity, behaves like alpha n, say, constant alpha n that depends only on dimension times affine surface area to the n plus 1 over n minus 1. Okay, so if we compare these two results, we'll see the dependence on the body in this random approximation is the same as the dependence on the body in the best approximation. We'll see the dependence on the number of vertices of the polytope is the same in the random approximation as in the best approximation. So the only potential difference is again in this constant, the dimension dependent constants that I had called dn here and that I had called alpha n here. So of course, because we are having here the best approximating result, of course, alpha n is smaller or equal than dn. But actually not by much, namely dn is smaller or equal than alpha n 1 plus log n over n. So as the dimension increases, alpha n and dn are almost the same. So in that sense, random approximation is almost, in that sense, random approximation is almost as good as best approximation. Okay, so now I have 5 more minutes, but it does probably not make much sense to continue much further. I just maybe want to mention some things that we recently did with Carsten and Matthias. So what I just told you was that we were having a convex body and we were choosing points on the boundary with respect to a probability measure, and the body was smooth enough. What we did, it had these smoothness properties. We can fit in, so to speak, a rolling ball inside and an outer rolling ball outside. So a natural question is, can we, and that's what we did with Matthias and Carsten, what happens when we choose points at random with respect to a probability measure, now not on a smooth bodies, but so to speak, at the so to speak opposite convex body, was not at the other situation. So we choose points at random on the boundary of a polytope. So you have a polytope and we choose at random points on the boundary of the polytope, take the convex hull, and that will give us then a random polytope that approximates the original given polytope. And the question is, so what we looked at is the expected volume, the expected number of vertices, the expected number of facets, the expected number of k-faces. And we were able to do that in the case of some specific polytopes, namely simple polytopes, like the cube, like indicated in this picture. But I can't go in the details, so I stop here. So thank you.
Okay, thank you very much, Elisabeth. Questions, please. I have a question on the previous page, please. Yes, you said that dn we know, yes? So it's some specific constant, dn, right?
Yeah.
And it is very surprising that in such a very general situation, I mean, this best approximation due to Gruber, it is possible to estimate alpha n with such big precision, since you know dn, right?
Oh, yes, sorry about that. I should have mentioned that. Actually, one can determine this alpha n, and it has been determined with relative precision. and I should have mentioned this, namely that was done by Mankiewicz and Carsten. They showed that alpha n is of the order n. So we, in our result here, we have a description of the dn in terms of the gamma function, and then this one can estimate and see that this is of order n. So that's not hard, but that's actually hard to determine in this best approximating result, to determine this alpha n. It's related to the Delaunay tessellations.
Tessellation.
Voronoi tessellations, but it has been determined, and it is of order n, and that was done by Mankiewicz and Schütt.
Mm-hmm. Oh, it's surprising in such a general situation. Yes. Okay.
Yeah, it is. Yeah. Mm-hmm.
And have you decided the regime when not only n but also dimension goes to infinity? For when you consider the points on the boundary, just for the ball, for the cube?
To look at the situation when not just the number of points, that is capital N, but also dimension of infinity. No, we have not looked at that, but no, we have not specifically looked at that, but it's always like so that in a sense, you know, we assume that dimension is large. Like for instance, when I say dn is of the order n, then this is for large n.
Okay.
But we have not looked at the asymptotics as n goes in, as little n goes in.
But such formulation is popular now, as far as I know.
Okay, good.
Okay.
Okay.
Okay, more questions? Okay, if not, Elisabeth, thank you very much. It was a very great, really great pleasure listening to your lectures. Very interesting, and I have learned many things. Now I understand the structure of the boundary of convex body much more than before, and I think I have more intuition now. Thank you very much for this. And I hope maybe next fall we will organize this semester offline, and so I hope it will be a good reason for you to come.
That would be lovely. That would be wonderful. So thank you so much again for doing this, and thanks for it's very late for you guys, and it's a weekend, so it's not so thanks for being there. So yeah, bye.
Okay, thank you. Bye.